Have you ever wondered what the sun really is, the giant, bright sphere that lights up our world every day? This celestial body, our nearest star, has been a subject of fascination and study for centuries. It's not just a light source, but the very engine of life as we know it. It fuels the process of photosynthesis in plants, which in turn produces the oxygen we breathe. The sun's warmth helps regulate our planet's climate, making life possible. Since ancient times, it has been revered and worshipped, and even today, it continues to be a central object of scientific inquiry. We have come a long way in understanding the sun, yet it remains a mystery in many ways. It's a burning ball of gas, a nuclear furnace where hydrogen is transformed into helium. As it turns out, the sun is far more than just a bright light in the sky. So how did this colossal fiery ball come into existence? Let's take a journey back in time, some 4.57 billion years ago, to the birth of our sun. Our story begins with a massive molecular cloud, composed mainly of hydrogen and helium, a floating cosmic nursery of sorts. This cloud wasn't stable. The delicate balance between the pressure from within and the gravity pulling it together was disrupted, possibly by the shock wave of a nearby supernova. The cloud began to collapse under its own weight. As the cloud collapsed, it started to spin, conserving its angular momentum. This spinning, along with the increasing pressure, heated up the core of the cloud. The intense pressure and heat at the core ignited nuclear fusion, the process that powers the sun. The fusion of hydrogen atoms created helium and released a tremendous amount of energy, causing the core to shine brightly. The surrounding gas and dust, drawn in by the gravity of the growing star, formed a spinning disk around it. Now, you might be wondering, where do the planets come into the picture? Well, that's where this spinning disk of gas and dust comes in. The heavier elements, which included metals and silicates, began to stick together, creating clumps of matter. Over time, these clumps coalesced and grew into the planets, moons, asteroids, and comets of our solar system. Meanwhile, at the heart of this cosmic ballet, the core of the collapsing cloud continued to gather mass, growing hotter and denser. The nuclear fusion at its heart became more and more vigorous until it finally reached a steady state. The energy produced by the fusion pushed outward, balancing the inward pull of gravity. This equilibrium marked the official birth of our sun, a main sequence star. And thus, our sun was born, marking the dawn of our solar system. Now that we know how the sun came into existence, let's delve into what makes it tick. The sun, our closest star, is a hotbed of activity and energy, a powerhouse that fuels life on Earth. At its core, the sun is predominantly composed of hydrogen and helium, the two lightest and most abundant elements in the universe. But it's not just the elements that make the sun interesting. It's what happens to them. The sun's core is the site of a process known as nuclear fusion. This is where hydrogen atoms under immense pressure and temperature combine to form helium, releasing a tremendous amount of energy in the process. This energy radiates outward from the core through the sun's outer layers and eventually reaches Earth as sunlight. But it's not only light that this energy takes the form of. It also produces neutrinos, subatomic particles that zip through the universe almost undetected. As for the sun's size, it's colossal. If you were to fill the sun with Earth's, you could fit over 1 million inside it, and its temperature, a scorching 15 million degrees Celsius at its core. Yet despite these mind-boggling numbers, our sun is considered an average star in terms of size and temperature. Here's another intriguing fact. The sun is halfway through its main sequence stage. That means it's been burning hydrogen into helium for about 4.6 billion years, and it's got about the same amount of time left before it exhausts its hydrogen supply. At that point, it will begin to evolve into a red giant, but that's a story for another time. The sun, in all its fiery glory, is the powerhouse of our solar system. It's a ceaseless nuclear reactor, a beacon of light and heat, and the gravitational anchor that keeps our planet in a stable orbit. It's a testament to the extraordinary processes that occur in the universe every second of every day. What does the future hold for our fiery sphere? As it turns out, our sun is midway through its life and is currently in what astronomers call the main sequence phase. This phase, which lasts about 10 billion years, sees the sun continuously converting hydrogen into helium, releasing an incredible amount of energy in the process. However, in about 5 billion years, the sun will begin to run out of hydrogen. This will mark the beginning of the end for our star. As the hydrogen supply dwindles, the core of the sun will contract and heat up, causing the outer layers to expand. The sun will then swell into a red giant, becoming hundreds of times larger than its current size. This transformation will have profound effects on the inner planets of the solar system. Mercury and Venus will likely be swallowed by the sun's expansion. Earth's fate is less certain, but it's possible that our planet could also be engulfed. Even if Earth manages to escape this fiery fate, the intense heat from the red giant sun will make our planet uninhabitable. The red giant phase will last for a few 100 million years. After that, the sun will shed its outer layers, creating a planetary nebula and leaving behind a hot, dense core known as a white dwarf. This white dwarf will slowly cool over billions of years, eventually fading to a black dwarf. Though the sun's demise is billions of years away, it's a reminder of the transient nature of stars and planetary systems. Each star we see in the night sky has its own life cycle, and our sun is no different. It's a sobering thought, but it's also a testament to the incredible dynamic universe we live in. After all, it's the life and death of stars that have given rise to the elements and planets that make life possible. How do we learn all this about an object that's 93 million miles away, you might ask? Well, it's all thanks to a combination of Earth-bound solar observatories, space missions, and advanced telescopes. Observatories on Earth provide a constant watch on the sun, employing a variety of instruments that measure solar radiation across a wide spectrum. These observatories help scientists monitor solar activity, track sunspots, and even predict solar storms that could impact our planet. But to get up close and personal with the sun, we need to venture into space. Several space missions have been launched with the specific aim of studying our star. One of the most notable of these is NASA's Solar Dynamics Observatory, or SDO. Since its launch in 2010, the SDO has been continuously observing the sun, capturing detailed images and data that have greatly advanced our understanding of complex solar activity. Another significant mission is the Parker Solar Probe, also launched by NASA. This daring mission is designed to swoop within 4 million miles of the sun's surface, far closer than any spacecraft before it. The probe is helping scientists unlock the mysteries of the sun's corona, that elusive outer atmosphere that is surprisingly hotter than the sun's surface. And then there are the advanced telescopes, both on Earth and in space, that allow scientists to observe the sun in unprecedented detail. For example, the Daniel K. Inouye Solar Telescope in Hawaii, which captured the highest resolution image of the sun's surface ever taken. In the end, studying the sun is a collaborative effort involving a multitude of tools and a global community of scientists. Each new discovery, each piece of the puzzle, brings us closer to understanding our star and its influence on our planet. Our understanding of the sun continues to evolve, with new discoveries illuminating our place in the cosmos. So let's revisit what we've learned about our nearest star. We began our journey by delving into the sun's formation almost 4.57 billion years ago from a collapsing molecular cloud, primarily composed of hydrogen and helium. We then explored its intriguing characteristics, from its core where nuclear fusion transforms hydrogen into helium, to the radiant energy it emits into space. We also cast a glance into the future, predicting the sun's evolution into a red giant, its inevitable engulfing of the inner planets, and its final transformation into a white dwarf. Lastly, we discussed the various ways scientists study this fascinating star, from early space missions to modern solar observatories. The sun, our closest star, is not only a source of light and life, but also a key to understanding our cosmic origins and destiny.